Mechanics, a foundational branch of physics, unravels the fundamental principles governing the motion and behavior of physical objects, from the celestial bodies in the cosmos to the minutest particles in the quantum realm. It serves as the cornerstone of classical physics, providing the mathematical framework to describe and predict the dynamics of diverse systems. Let us embark on a journey through the landscape of mechanics, where the laws of motion and the principles of forces paint a vivid portrait of the physical world. Newton's laws of motion. At the heart of classical mechanics lies Sir Isaac Newton's triumvirate of laws that govern the motion of objects. The first law, often referred to as the law of inertia, states that an object at rest remains at rest, and an object in motion continues in a straight line at a constant velocity unless acted upon by a net external force. The second law relates the acceleration of an object to the net force acting upon it and its mass, expressed elegantly through the equation F equals ma. The third law, the law of action and reaction, posits that for every action, there is an equal and opposite reaction. Kinematics. Kinematics, the study of motion without regard to the forces causing it, charts the spatial and temporal aspects of objects in motion. Position, velocity, and acceleration become the protagonists in this narrative, with equations describing the intricate paths traced by objects as they journey through space and time. Dynamics and force. Dynamics steps onto the stage when forces come into play. Forces, interactions that cause changes in motion, are scrutinized through Newton's second law. From the gravitational pull that keeps planets in orbit to the tension in a taut rope, forces shape the trajectories and behaviors of objects in the mechanical ballet of the cosmos. Energy and work. The concept of energy introduces itself as a fundamental currency in the realm of mechanics. Whether potential energy stored in an elevated object or kinetic energy manifested in motion, energy undergoes transformations as objects interact. The notion of work, the transfer of energy through the application of force over a distance, becomes a pivotal concept in understanding the dynamic interplay of forces in motion. Momentum and collisions. Momentum, the product of an object's mass and velocity, emerges as a conserved quantity in the absence of external forces. It becomes a key player in understanding the outcomes of collisions and interactions between objects. Conservation of momentum, an enduring principle in mechanics, guides the analysis of diverse scenarios, from billiard ball collisions to celestial dynamics. Rotational motion and angular momentum. As the mechanical narrative extends to rotating bodies, angular motion and angular momentum take center stage. Torque, the rotational analog of force, dictates the rotation of objects. Conservation of angular momentum becomes a guiding principle, influencing the behavior of spinning tops, planets, and galaxies. Fluid mechanics. Beyond the realm of solid objects, mechanics extends its reach to fluid dynamics. Fluid mechanics explores the motion of liquids and gases, introducing concepts such as viscosity, pressure, and Bernoulli's principle. Whether describing the flow of a river or the aerodynamics of an aircraft, fluid mechanics enriches the scope of mechanical principles. Elasticity and deformation. Materials, subject to external forces, undergo deformations and exhibit elasticity. The study of how materials respond to applied forces falls within the domain of elasticity. From the stretching of a rubber band to the bending of beams, elasticity elucidates the mechanical behaviors of materials. Friction and resistance. The influence of friction, a force resisting motion, adds a layer of complexity to mechanical analyses. Whether exploring the sliding of objects on surfaces or the dynamics of vehicles, friction becomes a crucial factor in understanding real-world mechanical systems. Advancements in computational mechanics. In the contemporary era, computational methods and simulations empower engineers and physicists to model complex mechanical systems. Finite element analysis, molecular dynamics simulations, and computational fluid dynamics offer insights into the behavior of structures, materials, and fluids under various conditions. In essence, mechanics is the orchestration of motion and forces in the grand symphony of the physical universe. It is the science that breathes life into the dance of celestial bodies, the motion of vehicles, and the subtle interplay of particles. From the timeless principles laid down by Newton to the intricate analyses of modern computational methods, mechanics stands as a testament to humanity's quest to understand and manipulate the mechanical essence woven into the fabric of reality.